Okay, yesterday we have proved limit x tends to 0. Limit x tends to 0 e raised to x minus 1 upon x is equal to 1. We have proved this. Now you prove limit x tends to 0 a raised to x minus 1 upon x is equal. Find out. Okay, answer is log a to the base. Now find out this. Limit n tends to infinity plus infinity 1 minus 1 upon n raised to minus n. I think we have done it somewhere in the process, but you establish this. I think we have done it yesterday. This is also equal to E. Okay, so now we have already defined what is derivative of function. Maybe just to recap, limit x tends to c f of x minus f of c upon x minus c is equal to f dash of c if exists and is finite. Okay, so this is what is derivative. Differential in the value of the function or differential in the value of the input as they go together, as they try to come together. So find derivative of. Now this is what whatever this we are writing here is also referred to as d by dx of f of x at c. Whatever this notation we have written here is also this, and this is exactly same. This is derivative with respect to x of function f of x evaluated at c is this limit. So find d dx of e raised to x using first principle. Derivative of e raised to x with derivative of e raised to x with respect to x. Sometimes this couple of versions of this might not be handy every time. Therefore, limit, suppose you have function f of x minus or let me do it positive first, f of x plus h minus f of x. That means the difference in the two values of x is equal to h divided by f of x plus h minus x is h as h tends to 0. This and this is exactly same. Okay, and we can call this as f dash of x. The differential becomes 0, is tending to 0. Therefore, you can use, this is also dy by dx, dx of f of x. Another version, so you are adding something to f of x. So maybe you are going towards right hand side. H is positive, you are referring to x. Suppose this is your function, this is your x and x plus h. This is x plus h. So you are going towards right hand side. Now if I want to go to left hand side, this function can be written as, this limit can be written as, again h tends to 0. I want to keep this quantity positive. How do we write it? The bigger minus the smaller. So bigger is f of x minus f of x minus h divided by h is equal to f dash of x. So this is from left hand side. I mean x minus h you are evaluating and taking this point near x. Okay, these two ways you can use the definition of derivative to evaluate derivatives of different function. So maybe in our case right now here we will use this definition. So this is equal to limit h tends to 0 f of x plus h. F of x plus h is e raised to x plus h minus f of x, that is e raised to x divided by h. We want to evaluate this limit. Now we will process. This is equal to, you can take out e raised to x common, limit h tends to 0 e raised to x inside bracket e raised to h minus 1 divided by h. Now we are evaluating for h. H is a variable. H is moving from little away from x to x. So that is the differential. We are making it equal to 0. That is the distance between the moving point and x, which is tending to 0. So this is a limit to be evaluated for h tending to 0. Therefore, limit e raised to x as h tends to 0 into limit e raised to h minus 1 upon h as h tends to 0. We have applied the limit of product is product of the limits, and we are assuming here that e raised to x is a continuous function and is well behaved. There will exist the limit. Okay, it is not undefined or positive infinity or positive negative infinity. So this limit is e raised to x, and this limit we have proved equal to 1. Therefore, the answer is e raised to x. So d dx of e raised to x is e raised to x. Understood? Next. D dx of a raised to x. Find. Combining the previous work that we have done, we will get this limit as a raised to this derivative as a raised to x into log a to the base e. Next, find d dx of log x to the base e. Find derivative of function log x. Okay, so let us use the first definition again, x plus h value. So this is equal to limit h tends to 0 f of x plus h, that is log x plus h to the base e minus log x to the base e upon h, right? Okay, therefore, using the logarithm property, we can limit h tends to 0 log x plus h upon x to the base e 1 upon h, which is equal to limit h tends to 0 log to the base e 1 plus h upon x raised to 1 upon h. Okay. Now, okay, we can say that logarithm is a continuous function. To the base e is limit 1 plus h by x raised to 1 upon h, h tends to 0. Okay. Now x is going to be a fixed point at which we are going to evaluate this limit. So for all practical purposes, we are going to evaluate the limit at specific value of x, maybe c or x naught, whatever. So what is changing in this is h and not the x. Therefore, x is going to be constant. X is constant means we are evaluating the derivative of the function at that x. Therefore, it is constant. It is not moving. Okay. But h means the distance from the neighboring point with respect to fixed x. So this is fixed x. So we should deal with that like this. Logarithm to the base e limit h tends to 0, maybe 1 plus h by x, where x is constant. So 1 plus a small only, because h is tending to 0 and x is constant fixed. Therefore, this quantity will tend to 0. So this is 1 plus a small raised to x by h. So that we can put h by x as t. Okay. And then we are changing value, therefore we have to take x root. So if we simplify this, we get this. Okay. So now maybe because doing it for the first time, we substitute. Let h by x is equal to t. Therefore, as h tends to 0, t tends to 0. Correct? Therefore, this becomes limit to the base, sorry, not limit, logarithm log to the base e limit t tends to 0, 1 plus t raised to 1 upon t whole raised to, now I can, power function is also continuous, so I can do it like this. This is also acceptable. That is why that rule that we have developed is very important. I mean, we can just flip log and function, limit and function, and flip the sequence if they are continuous. Now this is in our control. This is what we have already established. So therefore, log of to the base e, we said this is e raised to 1 upon x. Therefore, this is 1 upon x log e to the base e is equal to 1 upon x. So derivative is 1 upon x. Reduce the size and keep it in front of you so that you find the ddx of log x to the base a. Now, what will be the derivative of k times f of x, constant times f of x? Limit what? X or h tends to 0, f of k times f of x plus h minus k times f of x upon h, which is equal to limit h tends to 0 k into f of x plus h minus f of x upon h, which is equal to limit k h tends to 0 into limit h tends to 0 f of x plus h minus f of x upon h, which is equal to k, limit of k, h tends to 0 is k, and this is f dash of x. So derivative of constant times function is constant times derivative of function. So now here what are we doing? ddx of log x to the base e we know. So ddx of log x to the base e divided by log a to the base e. That is what this function is, and this is constant. Therefore 1 upon log to the base e, log a to the base e is a constant which is coming out, and then derivative of log x to the base e is 1 upon x. But it also can be remembered as 1 upon x log e to the base a. I mean, whether you are putting it in the denominator or numerator, you need to be very clear about it. You cannot get confused. Log a to the base e, or you can remember it like 1 upon x log a, derivative of log x to the base a. So these are some basic derivatives. I think we have done derivatives of trigonometric function also, that is sine, cos and tan. Okay, so now we have to concentrate on few results on derivatives, which we will do now. Theorem. Let I be an interval. Let f be defined from I to I. Let C belong to I. If 1, f is differentiable at x is equal to c, then 2, f is continuous at x is equal to c. Okay, so what is this theorem? Differentiability implies continuity. That is what this theorem is. So write down complete correct proof of this theorem. We want to show f is continuous at x is equal to c. Therefore, consider limit x tends to c f of x minus f of c. We want to check this limit, and if it is equal to 0, then we are done. Okay, so this is equal to, now limit x tends to c, we can always divide and multiply by non-zero real number, x minus c. Okay, this always can be done because x is not equal to c. Therefore, I should have put this bracket outside. Limit x tends to c, f of x minus f of c upon x minus c into limit x minus c as x tends to c. I can do this provided this exists and this is existing and they are finite. So I will cross check. In mind first I will cross check whether they exist and are they finite or not. And it is given that this exists and is finite. So this exists and finite and is finite. Definitely yes. So some real number, value of this is some real number into x tends to c, x minus c 0. Therefore this limit, whatever we are considering, we have proved it to be equal to 0. That implies limit x tends to c f of x is equal to f of c. By definition, it's continuous. Very important, differentiability implies continuity. I mean, more or less you have written in this way only, but this is the simplest way of expressing it. Question: is converse true? If a function is continuous, will it be differentiable at x is equal to c? Is converse true? Why? 2 मिनिटं विचार करून मला उत्तर दाखवा तुमचं काय आहे ते. Okay, if we want to prove theorem, we have to write the proof, and if we want to disprove, one counter example is good enough. If continuity implies differentiability, if that statement has to be true, but it is not true because we have many examples by which we can prove that function is continuous but not differentiable. And the most easy function to imagine is mod x. Y is equal to mod x. Okay, as x tends to 0. So let us check, let us get into our calculus and check what happens exactly when we try to find out the limit. So limit x tends to 0, f of x minus f of 0 divided by x minus 0. This is what we want to evaluate. So first we will evaluate. So this is derivative of the function at x is equal to 0. Our function is mod x. Therefore, we will first limit right hand derivative. We will try to find out 0 plus. So x is approaching 0 from positive side, from this side, 0 plus. Function is mod x minus mod 0 upon x minus 0. So we are actually talking about limit x tends to 0 plus mod x upon x, right? Now x is tending to 0 from positive side, therefore x is positive, therefore mod x is x, limit x upon x, x tends to 0, and x upon x is 1, therefore limit 1 x tends to 0 is equal to 1 from positive side, okay. So limit from positive side is 1. Now let us check what is limit from negative side. Limit x tends to 0 minus, that means I am going to 0 from the negative side of 0, okay. Mod x upon x, which is equal to, if x is negative, then mod x is opposite of x upon x, which is equal to limit x tends to 0 minus 1, which is equal to -1, and these two guys are not equal, okay, and the value of the function is 0, okay. So left hand derivative and right hand derivative at x is equal to 0 is not the same, and therefore this limit does not exist. For mod x, and hence it is not differentiable. Is it continuous? Yes, we know that for every x it is well defined. Therefore, y is equal to x is continuous, but not differentiable. Okay, so this is important. Next, signum function y is equal to check differentiability at x is equal to 0. Signum function. जमेल का? Check differentiability of signum function at x is equal to 0. What is signum function? If x is greater than 0, y is 1. At x is equal to 0, y is 0. And if x is less than 0, y is equal to -1. Okay, signum function. If you want to use definition of derivative, f of x is +1 minus f of 0 is 0. So 1 minus 0 upon x minus 0 is 1 upon x. If x tends to 0 from positive side, answer is +infinity. From negative side, f of x is going to be -1 minus 0 upon x minus 0. So -1 upon x. Now the x values that we are going to put are going to be negatively signed. Therefore, that minus minus will get cancelled. Hence, this limit also will tend to +infinity. Both the limits are equal. Right hand derivative and left hand derivative both are equal but are not finite. Therefore, differentiability fails for signum function. That is what we are proving. So, this is analytical way of checking the differentiability. Just use the definition of derivative. And geometrically also, if you know the graph, you can cross check your observation and say that at x is equal to 0, continuity is not there, differentiability is also not there. Okay. So that is good. Now let us begin with algebra of derivatives. Vertical line complete. Okay. So I can start. चला okay, now let me write down the next theorem. 50%. Algebra of derivatives. Why do we want to do this? Because suppose we have two functions additive. Suppose x plus log x, f of x is equal to, and I want to find out f dash of x. Then what do I do? Shall I take derivative of each one of them and add them? I don't know whether it is correct or not. If I have g of x, which is product of two functions, x log x, what do I do? Shall I find out derivative of this g of x by multiplying the derivatives or something else? We do not know. That is why we want to develop the algebra of derivatives. Essentially addition, subtraction, multiplication, division. What do we do? And hence, if we have a complex function, or a complex function by mean a composition of function or addition of function or multiplication of functions, then if we have these rules with us, we can find out the derivatives very quickly and they will be correct. If we in general prove these laws for algebra of derivatives. So that is the purpose of doing this. We did algebra of limits because limit was the new concept which we have introduced. Once introduced a new concept, how is it well behaved for addition, multiplication or not? It is our responsibility to check. So the first result. Let f comma g be defined from I to R. Let C belongs to R. If 1, f is differentiable at x is equal to C, 2, g is differentiable at x is equal to C, then f plus g is differentiable at x is equal to C, and 4, f plus g dash at C is equal to f dash of C plus g dash of C. So addition, if it is an addition function, then derivative of addition function is addition of derivatives. That is what we are trying to prove. Take your time and write the complete correct proof of this. Consider limit x tends to C, f plus g of x minus f plus g of C upon x minus C is equal to limit x tends to C, f of x plus g of x minus f of C minus g of c. By definition, x minus c. Limit x tends to c, f of x minus f of c upon x minus c plus g of x minus g of c upon x minus c. Which is equal to limit x tends to c, f of x minus f of c upon x minus c plus limit x tends to c, g of x minus g of c upon x minus c exists and finite by whatever statement 1 by 1 and exists and finite by 2. Therefore, exists and finite. Hence, by definition, f plus g is differentiable at x is equal to c and is equal to f dash of c plus g dash of c. Done. Next. So if addition is done, then subtraction is also done. Therefore, we are doing now multiplication. Next theorem is to let f comma g be defined from I to R. Let c belong to I if 1. F is differentiable at c and g is differentiable at c. Let me see if I can do this quickly. Copy. जास्तीच वेळ लागतो जरा कुठे कॉपी पेस्ट करतो तो जाऊ finally I have achieved it without c, which I will write. And this ellipse is creating problem. Okay, f is gone, which I will write. G, sorry. G is differentiable at x is equal to c. Then three f into g is differentiable at x is equal to c, and for f into g of dash of c is equal to, we will find this out. Okay, so you start proving independently, check what you get here eventually, and we will create a rule for multiplication. This is very, very important. Proof. Consider limit x tends to c, f dot g times x minus f dot g of c upon x minus c is equal to limit x tends to c f of x into g of x minus f of c into g of c upon x minus c. Now, if we want to use this statement number 1 and statement number 2, we need them separate. Therefore, this is equal to limit x tends to c f of x into g of x minus f of x into g of c plus f of x into g of c minus f of c into g of c. So I am not changing the numerator, I am keeping it same. Only little bit of algebra here and there, which is equal to limit x tends to c, f of x is taken common, into g of x minus g of c upon x minus c. Now let me do it two steps in one step. Limit x tends to c, I can take g of c common, inside bracket f of x minus f of c upon x minus c. Okay, so I can again one more time I can split this limit, and limit x tends to c f of x, that is f of c, limit x tends to c g of x minus g of c upon x minus c, which is g dash of c plus g of c into f dash of c. That is what, yes, that is what you eventually get, and hence it is differentiable, and 3 and 4 proved. 3 and 4 proved, I have to write, complete that 4 over there. 4 is f of c into g dash of c plus g of c into f dash of c. Good. Third, let us do the reciprocal theorem first, and hence ratio theorem will be achieved. So, reciprocal theorem. Let f be defined from I to R. Let C belongs to R. If one f is differentiable at x is equal to c, to f of c is not equal to 0, then 1 upon f of x is differentiable at x is equal to c, and 4 1 upon f dash of c is equal to, we will fill this later on and do this result. So I give you time. The game is consider. minus f of c upon f of c, f minus f dash of c upon f of c bracket square is the answer. Okay, so let us complete the product now. Any doubt, difficulty in this? It is a simple calculation using the previously defined concepts, etc. Okay. Next. Product. Next, product dollar ratio. That is our fourth. Let F be defined from I to R. Let C belong to I. If 1. F is differentiable at x is equal to c. 2. आता इथे f comma g पाहिजे. G is differentiable at x is equal to c. 3. G of c not equal to 0. Then 4. F by g of x is differentiable at x is equal to c. And 5. F upon g of x is equal to f dash of c minus f dash of c into g of c minus g dash of c into f of c upon g of c bracket square. चला लिहून टाका, आजचं काम संपलं.